When two black holes collide at a speed 10 billion times faster than any previous observation, they create extreme conditions that prove Albert Einstein's theory is correct. When the two black holes orbit each other in even closer orbits, gravitational waves are completely cancelled out. Einstein's general theory of relativity explains how black holes might affect precession. Precession occurs when a torque, such as the force of gravity, changes the spin axis orientation and the axis gradually reverses direction. The gyroscope's pole gently spins around in a circle. Einstein's theory, which came out in 1916, said that gravitational waves would be there, and now we can see them with our own eyes. The first direct proof of a fast precession in history has come, and these black holes clearly exhibited a wobble or twisting motion. Black holes have never previously shown us this phenomenon. Einstein calculated things like the speed of the wobble without enough scientific proof as part of his general theory of relativity. Nevertheless, his calculations were correct. A wobble's speed is 3 times per second. This is the first concrete confirmation of Einstein's prediction of black hole precession. Furthermore, the unprecedented collision between the two black holes provided conclusive evidence for this theory. These regions of space are also known as binary black hole systems, since they have a pair of black holes that orbit each other very closely. Professor Mark Hunnam of Cardiff University's Gravity Exploration Institute said, "We've long speculated that binary black holes can accomplish this. We have been trying to discover an example since the first gravitational wave detections. 5 years and 80 separate detections later, we finally got it." They decided that the black hole's spin most likely caused the noise at the highest limit allowed by general relativity. They didn't believe the results of an earlier study that found no precession. Einstein's theory is supported by the fact that the two stars smashed into each other and then merged. Scientists will now look for other black holes colliding in the universe to see if this really is a one-of-a-kind event, or they've finally found the roots of precession. Albert Einstein's general theory of relativity predicts precession like what we see in the GW 200129 system. This theory explains how large objects bend space and time in a way that we feel as gravity. Scientists think that the wobbling orbit of the binary system is caused by the fast spin of the black hole, which messed up space-time in such a big way. General relativistic precision has raised many eyebrows since its impact is significant. Before this, the fastest known case was a pair of neutron stars in orbit, called binary pulsars, whose orbit shortened over a period of more than 75 years. Albert Einstein's general theory of relativity has been proven correct for the first time by the 3 times per second shaking of merging black holes. A wobbling motion known as precession may emerge if the orbit or rotation of an object gradually changes over time. Precession refers to the gradual change of an orbit's geometry under the pull of gravity. This happens, as predicted by general relativity, when massive objects distort time and space. A few times a year, orbital wobbles or peaks between 2 nearby neutron stars occur. The influence of one black hole spinning at an angle of 90 degrees to its orbital motion was seen by researchers at Cardiff University in the United Kingdom, led by Mark Hunnam. They were studying a pair of black holes moving at 1/5 the speed of light. The gravitational wave GW 2001-29 was generated due to an event that included the merger of 2 black holes. This oscillation occurred 3 times per second, typical of classic precessional waves. Hunnam calls this the most extreme regime of Einstein's theory, when space and time change in ways that can't be explained approximately 10 billion times faster than seen before. In 2020, the precession was found through the reanalysis of data from 3 gravitational wave detectors in the United States and Italy. Using a more precise model of the gravitational wave signal, Hunnam and co-workers concluded that one of the black holes must be spinning at almost the maximum speed permitted under general relativity. Consequently, the priority of the system's orbit would switch. Astrophysicist Fabio Antonini of Cardiff University, who was not involved in the study, says the results have tremendous implications. He says that most theories about how black holes form involve stars falling in on themselves, but this can't explain why they spin so quickly and their orbits aren't lined up. Even light can't escape the overwhelming gravity of a black hole. Einstein's general theory of relativity says that black holes can't be told apart by anything other than their mass, spin, and electric charge. This is called the no-hair theorem. The no-hair theorem states that a black hole's mass, angular momentum, and electrical charge are the only observable properties of a black hole. Its name no-hair alludes to the fact that there aren't many distinctive features on a black hole. The complete fulfillment of this idea, however, has been hampered by magnetic fields. According to the no-hair theorem, a black hole's feeding of matter shouldn't alter its essential features, but the plasma clouds surrounding a black hole may create huge magnetic fields or get them by eating certain parts. To investigate, researchers utilized a supercomputer to simulate a black hole in a plasma set. Einstein's theory still holds, even if black holes have magnetic fields that last long. According to Bart Ripperda, a research fellow at the Center of Computational Astrophysics, the no-hair hypothesis is a cornerstone of general relativity, which can be disproved if and only if black holes have persistent magnetic fields. Using simulations, scientists found evidence that magnetic fields around black holes could evolve. The simulations show that the magnetic field lines around the black hole swiftly break apart and subsequently reconnect. The magnetic field would push pockets of plasma to the surface, where they would blow up and send debris flying around the air around the black hole. As Ripperda puts it, theorists never took this alternative because they always simulate black holes inside a vacuum, yet in many instances, plasma is present, and plasma may sustain and attract magnetic fields. Even so, research has shown that this mechanism could quickly reduce the magnetic field until it goes away completely, supporting the no-hair theory. Scientists were looking for problems with Einstein's theory of gravity, but instead, they found an image of a black hole that seemed to fit with his idea. A group of international scientists revealed the first image of the black hole at the center of our galaxy. The image is thought by scientists to provide evidence for Einstein's general theory of relativity. In 2019, the same tool, the Event Horizon Telescope, took the first ever picture of a black hole. An international group of scientists used the Event Horizon Telescope to take our neighborhood's supermassive black hole's first ever image of Sagittarius A. Einstein's general theory of relativity makes predictions, and a new postcard of the center of our Milky Way galaxy backs up those predictions, even if they were made over 100 years ago. These never-before-seen images provided fresh insights into how these gigantic black holes interact with their environment and have significantly increased our knowledge of what occurs at the very core of our galaxy. Albert Einstein predicted the existence of black holes a century ago, and they are regions of space with such extreme gravity that not even light can escape. For the last century, researchers have been trying to find holes in Einstein's general theory of relativity, but they have yet to find any. Observing the strongest effects of gravity near a black hole's event horizon might be used as a test of Einstein's general theory of relativity. Every cosmological experiment has confirmed Einstein's views on the behavior of matter near black holes. Sagittarius A depictions were another proof that Einstein predicted its symmetrical shape. Duncan Brown, a professor at Syracuse University who was not involved in the cosmic photo op, remarked in a press release, "It confirms that Einstein was accurate once again." In addition, Brown claimed that the gas is moving almost as fast as the speed of light, and that the image shows it swirling around the black hole at the galactic core. Scientists have been able to get pictures of supermassive black holes before. The black hole at the center of the Milky Way is 1,000 times smaller than the one at the center of the Messier 87 galaxy, which is very far away. As more and more photographs of black holes are taken, scientists may continue to search for flaws in Einstein's theory. Will Einstein's theory ever be debunked?